Good morning and welcome you all to this session of the course. Now we come to a thing which is known as degree of reaction, which is very important, degree of reaction. What is meant by degree of reaction? Now try to understand one thing. Again I will repeat the thing which I told you earlier in the fluid machines class when I discussed the hydraulic machines, the machines using water. Now one has to understand that any fluid machines has a rotor and a stator, okay, whether it is a turbine or it is a compressor or pump. Okay. So the basic purpose of this stator or the diffuser in a pump or compressor is to change the velocity to static pressure. But the question comes whether in a rotor the static pressure will change or not. First of all, try to understand in terms of pressure, static pressure will change or not. So static pressure will change in the rotor depending upon the rotor construction. If it is a radial flow machine type, rather I will tell machine type, that means the radial flow machine, automatically the pressure changes because of the centrifugal action of the centrifugal head, that is the centrifugal force. When the radial location changes, the peripheral speed is changing. So therefore this is manifested in terms of the increase in a static pressure. I explained so many times that a radial pressure gradient is imposed when the fluid has a tangential velocity and it changes its radial location. But in an axial flow machines, when there is no change in the tangential flow from inlet to outlet, not necessarily there will be a change in the static pressure. The change in the static pressure will depend upon the rotor design and construction. That means if we have to change the flow area, if you change the velocity relative to the rotor in flow, course of flow to the rotor passage, then only there will be a change in the static pressure, and that is the measure of reaction in a reaction turbine, that whether there is a change in the static pressure in the rotor itself or not. For example, in impulse turbine, if you remember a water turbine, that Pelton turbine, the water jet is striking the rotor, that is the Pelton wheel, at atmospheric pressure. Throughout pressure is same, there is no change in the pressure. This is known as impulse turbine. Whereas in Francis turbine, when it goes through the runner blade, there is a change in the pressure. Similarly, in the centrifugal pump, always there will be a change in pressure in the impeller. This is because of the radial flow in a rotating or tangential flow field. Similar is the case of centrifugal compressor. But in axial compressor, the question comes whether the flow passage changes in course of flow through the rotor, so that the relative velocity changes or not. I told you that if the relative velocity changes, in a sense that if VR2 is less than VR1, then we can consider that we think that there is a change in the static pressure, and when there is a change in the static pressure, there will be a change in the static temperature also. So therefore, whether there is a change in the static pressure or not, that we will call the machine is reaction type or not. Usually there is a change in static pressure and the static temperature while flowing to the rotor. VR2 is made less than VR1, and therefore the question of reaction comes, and the degree of reaction in this context is defined as this way. In terms of enthalpy it is defined. The change in enthalpy, let us consider per unit mass in the rotor divided by the change in the stage delta H rotor plus delta H stator. This is known as delta H stage. Since the enthalpy change for an ideal gas is equal to the Cp into change in the temperature, and since Cp is constant here, we are considering the ideal gas, it is independent of the temperature, we can cancel it out. In reality also the Cp does not vary much with the range of temperature. This can be written in terms of delta T, the static temperature change in the rotor divided by static temperature change in the stage, that means in rotor plus delta T stator. Now this is the degree of reaction. When there is no change in static temperature or static pressure, degree of reaction is 0. So degree of reaction is 0. For a reaction machine, there will be always a degree of reaction, since delta T rotor has got a value more than 0. So, this is the measure of the extent by which the total, the fraction by which the total change, that is total change in the static temperature of the stage is taking place to the rotor. Okay. Now, with this definition, let us now see the how we can find out an expression for this. Now, let us consider now again the definition, since we give this S for stage and rotor and stator, these things we will not write. So, simply we tell that A stands for stator for our convenience and B stands for rotor, and we write this definition as delta T. This is A, for example, you write, sorry, this you write rotor, this will be better, and this you write stator. Then you write delta A, delta T A plus delta T B. Okay. Now, you see that work done per unit mass is nothing but Cp into delta T stagnation. Now, if we make V1 is V3, now you see this diagram, we told that alpha 3 is alpha 1, but in our design V3 is made V1. Now, see that it approaches with some V1 from the earlier stage, then while it passes through the rotor, it gains energy and this V is increased, V2 is greater than V1. Then this V2 is again by the diffusion process, that means this is decelerated to get a rise in static pressure, is that means V3 is less than V2, is less than that, and it is also displaced more towards axial direction. This deceleration is made in such a way V3 comes back again to the original V1. If we make a design like that, that the absolute velocity at the discharge of the or at the outlet of one stage becomes equal to that of its inlet velocity at this stage. You understand? So that we can write V3 is V1. In that case, we can write delta, that means what is T total, T stagnation temperature at 3, for example T3T. Now, I write the total temperature T, here you see. Then T1T, T1T is T1 static plus V1 square by 2 Cp. Similarly, here you see T3T, the total temperature is T3 plus V3 square by 2 Cp. So, if V1 is V3, that means the dynamic equivalent temperature, okay, that means the velocity equivalent temperature are same. That means the difference in the total or stagnation temperature is difference in their static temperature. So, that delta T ST, that is the stagnation temperature, is delta T static, and here S is written, that is per stage. That means delta T stage, that means this is delta T stage, that is static temperature per of the stage is equal to the stagnation temperature. That means this can be written as delta T S, and this is nothing but the work done formula. That means if you remember that, this, what is this formula? U Vf into tan alpha 2 minus tan alpha 1. So, therefore, Cp delta Ts is given by this, correct? Bracket is there, there will be a bracket. Now, this is correct. Now, how to find out this for delta Ta? So, therefore, now I find out the value for delta Ta. Now, rotor, the energy is actually given in the rotor. So, W by M is written in terms of the total one, that means U Vf. Again I am writing tan alpha 2 minus, for your convenience, tan alpha 1, and this becomes is equal to Cp delta Ts, static temperature rise per stage, because the static temperature rise equal to the stagnation temperature. Now, if I write this W by M, that is U Vf into tan alpha 2 minus tan alpha 1 in terms of the static temperature change of the stator, I am not permitted, because stator static temperature, so entire energy used not to increase its static temperature, but at the same time to increase its velocity V2 square by V1 square. So, an energy balance in the rotor gives that rotor energy takes and the air static temperature is increased. This is the energy change due to the increase in static temperature, that is the static enthalpy rise plus the kinetic energy change. So, summation of these two from a steady flow energy equation is the energy input per unit mass basis. So, this is that. So, therefore, we can write Cp delta Ta is equal to UVF tan alpha 2 minus tan alpha 1 minus half V2 square minus V1 square. Now, you see V2 V1 from the velocity triangle. Now, from the velocity triangle, if you recall that V1 is what, if you see this triangle, so this is alpha 1. In terms of alpha 1, the cosine of alpha 1 is which one? Vf by V1. So, V1 is Vf by cosine alpha 1 and V2 is Vf. Vf is same as I have told earlier by cosine alpha 2. That means, this is Vf by cosine alpha 1, this is Vf by cosine alpha 2. So, with this thing I can write this equal to UVF tan alpha 2 minus tan alpha 1 minus half, this is Vf square, I take Vf common, Vf square into 1 by cosine, that means sec square alpha 2 minus sec square alpha 1. I think I am correct, sec square alpha 2. Now, you know again from the trigonometric relationship that sec square alpha minus tan square alpha equal to 1. That relationship at the school level you know. So, therefore, if you use that, this becomes UVF tan alpha 2 minus tan alpha 1 minus half Vf square, then this is also tan square alpha 2 minus tan square alpha 1. Now, I use this expression for Cp delta Ts, that is stage, and this expression delta Cp delta Ta for the rotor. This stage means delta Ta plus delta Tb. Then I can write the omega, which is equal to delta Ta by delta Ts as Cp cancels. So, therefore, this becomes equal to UVF tan of alpha 2 minus tan of alpha 1 minus half Vf square tan square alpha 2 minus tan square alpha 1 divided by the total stage, which we derived earlier, UVF tan of alpha 2 minus tan of alpha 1. This can be written as 1 minus, then Vf will cancel, that is Vf by 2u, and this will be tan of alpha 2 plus tan of alpha 1. Okay. Now, this is the definition. Okay. Now, this tan of alpha 2 plus tan of alpha 1. So, this is the definition of final definition of the 1. But now, if we change it to tan beta 1, then what we call that we already have found out this expression. If we see this expression at the beginning, which we found out that tan alpha 1 tan alpha 2 minus tan alpha 1 is equal to UVF. Okay, that what we did, just a minute, U by Vf by U is, what is that one? The very beginning, which we did. If you see that thing at the beginning, U by Vf, UVF is tan alpha 2 minus tan alpha 1 and tan alpha 2 minus tan beta 1. So, if tan alpha 2 plus tan alpha 1, if you remember this, U by Vf again I am writing tan alpha 1 plus tan beta 1 from the geometry, that is from this one we initially write, yes, this one. If you add these two, twice u by Vf is tan alpha 1 plus tan alpha 2 plus tan beta 1 plus tan beta 2. So, again I am going to write that for your benefit, tan alpha 1 tan beta 2. So, therefore, we write twice u by Vf from here is tan of alpha 1 plus tan of alpha 2 plus tan of beta 1 plus tan of beta 2. Now, if tan alpha 1 plus tan alpha 2 is substituted or is just eliminated in terms of tan beta 1, tan beta 2 from this, that means tan alpha 1 plus tan alpha 2 is written twice u by Vf minus this. If you write here, then finally you get an expression for the degree of reaction. You get finally an expression. If you do it, it is very simple. There is nothing difficult. You get an expression is equal to Vf by 2u into tan of, that is nothing great, beta 1 plus tan beta 2. That means simply you make tan alpha 1 plus tan alpha 2 2u by Vf minus tan beta 1 minus tan beta 2, and then make it clear, 1 minus 1 will cancel. So, you will see a result like that. This is the final expression for the degree of reaction. Now, let us make an case study that where we get a 50% degree of reaction. That means 50% or half of the total enthalpy or static temperature rise of the stage takes place in rotor. In that case, we get a very good result that u by Vf is equal to tan beta 1 plus tan beta 2. Now, this is one very important result. Now, if you compare this result with this results, u by Vf is tan, now you compare this with the result earlier, that means this one, u by Vf is tan alpha 1, u by Vf is tan alpha 1 plus tan beta 1, and that just now I wrote, earlier also I wrote, this is simply from the geometry. So, with this three relationship you get very beautiful result. When you equate this with this, that means we get alpha 1 is beta 2, and if we equate this with this, then we get alpha 2 is equal to beta 1. And as we told earlier that alpha 1 is alpha 3, that alpha 1 is alpha 3, then that becomes equal to alpha 3. So, this is one very important result. What does it give? This important result gives, if I write here that these results, if I write here alpha 1 is beta 2 is alpha 3 and alpha 2 is beta 1, then you see what we get. Alpha 1 is beta 2, beta 2 is the outlet angle of the blade, rotating blade, rotor blade, and that becomes equal to alpha 1. What is alpha 1? Alpha 1 is this one, which is alpha 3, that means outlet angle of the stator blade. That means the outlet angle of the rotor blade equals to the outlet angle of the stator blade. Again beta 1 is the inlet angle of the stator blade, which becomes is equal to alpha 2. Alpha 2 is the absolute velocity angle at the outlet of the rotor, which exactly equals to the inlet angle of the stator blade. That means the inlet angle of the rotor blade is equal to the inlet angle of the stator blade. So, therefore, inlet angle of this rotor blade is equal to the inlet angle of the stator blade, outlet angle of the rotor blade is equal to the outlet angle of the stator blade. So, they are cambered in the opposite direction, but their inlet outlet angles are same. The inlet angle of one blade is equal to that of the other, and outlet angle of rotor blade is equal to that of the stator blade. This type of design of blade is known as symmetrical blading, and it is easy for construction. So, therefore, we see for a 50% degree of reaction 0.5 we get a symmetrical blading. That means the inlet angle of the rotor and stator blades are same. Similarly, the outlet angle of the stator and rotor blades are same. Okay, thank you. Today up to this.